Hello, welcome to EE405 Introduction to Robotic Manipulator, and I'm Sang Lee, teaching assistant of today's session. If you have any questions regarding today's session, please feel free to interrupt me. Today we will start with the fundamentals of robotic kinematics. First, we'll learn how to visualize a robot using URDF, which defines the robot's structure. Next, in for kinematics, we calculate the end effector's position and orientation from the joint values. Then, in inverse kinematics, we do the opposite, finding the joint values for a desired end effector pose. And finally, we'll look at direct teaching, where the user physically guides the robot and records the motion for later use. So, about the experiment 1. Let's talk about URDF, which stands for Unified Robot Description Format. URDF is a standard XML-based format used to describe the robot model. In a URDF file, we define the rigid parts of the robot, which are called links, and we also define the joints that connects these links. Each link can include its inertial, visual, and collision properties. An important point is that all frames in a URDF are expressed relative to the joint frames. So, by combining links and joints in URDF, we can create a full description of the robot's structure. To visualize URDF files, we can use a package called Visor. To install it, we first need to set up some build tools using PIP, and then we install Visor itself. Today's first task is to visualize our URDF with controllable sliders. To do this, you should first extract the zip files you downloaded from KLMS into the source directory. The URDF file, for example, is located in the manipulation experiment /resources/JetRover description folder. Next, moving into the manipulation experiment directory and run the script python3 urdf.py. After you run this command, the terminal will print out an HTTP address. If you press Ctrl plus click on that address, Visor will open and show you the robot model. Next topic is about forward kinematics. Forward kinematics means computing the pose of the end effector, TEE, from the given joint angles, Q. In other words, if we know the joint values, we can calculate where the end effector is located in space. To compute this, we multiply a sequence of transformation matrix from the base frame through each joint and links until we reach to the end effector. So, forward kinematics gives us a direct mapping from the robot's joint angles to the end effector's position and orientation. In task 2, your goal is to calculate the end effector pose using random joint values. To do this, you will implement your own forward kinematics code inside the file kinematics.py under the manipulation experiment folder. We need to complete the function called forward kinematics. The input will be the joint angles in radians, and the output should be a homogeneous transformation matrix, which is a 4x4 matrix. After finishing your function, you can check the result by running the command python3 run_fk.py. This will verify whether your forward kinematics implementation works correctly. So here are a few notes for task 2. The transformation data and rotation axis for each joint are already provided. You can find them in the file kinematicsutils.py. When you implement your code, try to visualize the pose of each frame step by step from the lower joints to the upper joints. You also need to implement a function TQ that generates an SE3 transformation matrix from a single joint value. Finally, end effector pose can be computed by multiplying all of these SE3 matrices in order. Now let's move on to inverse kinematics. While forward kinematics calculates the end effector pose from the joint values, inverse kinematics does the opposite. It finds the joint values that achieve a desired pose. In other words, when the end effector pose is given, our task is to compute the joint angles Q. Since this problem is often difficult to solve analytically, we'll approach it using an optimization-based method. To solve inverse kinematics, we often define an error function. Here, we consider a simple 2D case with 3 joints. The error is split into 2 parts. First, the position error, which is the difference between the target position and the current end effector position. Second, the rotation error, which is the difference between the target orientation and the current orientation. Together, these form our kinematics error function, combining both position and rotation errors into a single vector. By minimizing this error, we can find the joint values that achieve the target pose. Previously, we defined the kinematic error in 2D. Now, let's extend this idea to the full 6D case. The error again has 2 parts. First, the position error, which is simply the difference between the target and the current end effector position in 3D. Second, the rotation error, which we express in exponential coordinates using the logarithm of the rotation matrix. Together, these form the 6D error function, combining both position and rotation into a single vector in R6. This error will be minimized in our optimization-based inverse kinematics approach. So to actually solve inverse kinematics, we treat it as an optimization problem. So our goal is to find the joint values Q that minimize the kinematic error function. And this is essentially a least squares problem, where we try to minimize the squared error between the current and end effector pose and the target end effector pose. One common approach is the Gauss-Newton method. In this method, we iteratively update the joint values using the Jacobian of the error function. Through repeated updates, the solution gradually converges to the joint values that achieve the target pose. So, in task 3, your goal is to compute the joint values that achieve the target end effector pose. You will implement your function in kinematics.py by writing the code for inverse kinematics. The inputs to this function are the initial joint angles in radians and the homogeneous transformation matrix of the target end effector. The output should be a dictionary that contains 3 things. First, the optimized joint angles in radians. Second, the position error in meters. And third, none if the optimization fails. For more details, you can check the annotations in kinematics.py. To implement inverse kinematics, we will make use of 3 main tools. First, JAX, which provides automatic differentiation. We'll use it to compute the Jacobian efficiently. Second, JAX-Lie, which allows us to calculate exponential and logarithmic maps on SO3. And third, SciPy, specifically its least squares solver, which we'll use to solve the optimization problem. By combining these tools, we can implement our inverse kinematics in a straightforward way. For task 3, here's the guideline for implementing inverse kinematics. First, re-implement your forward kinematics function using JAX, simply replacing NumPy arrays within JAX arrays. The second, implement the error function called error_fn. Third, get the Jacobian function by using JAX automatic differentiation. Next, define an initial guess for the joint angles. From there, generate a target pose by slightly perturbing the forward kinematics result. Then, use scipy.optimize.least squares to solve for the joint values that minimize the error. Finally, check your implementation by running Python 3 run ik.py. Finally, let's look at the last task, direct teaching. In this task, your goal is to save 4 server positions, each with an action duration of 2 seconds. We'll use control software to perform this teaching process. After recording these positions, the robot will be able to follow the trajectory that you created through direct teaching. To start direct teaching, first click on the arm icon on the desktop. This will open the control software. So on the left side, you can see the servo control area where you can adjust each servo position directly. On the right side, you'll find the action list, which records and stores the sequence of servo positions. Using this interface, we can create and save motions step by step, and then play them back as a trajectory. In the software, each servo is assigned an ID. For our setup, we have servos with IDs 1, 2, 3, 4, 5, and 10. Each servo has a position value ranging from 0 to 1,000. By adjusting these values, we can control the robot's movement at each joint and record specific poses for direct teaching. To save servo positions, first press the manual button to move the arm into the desired posture. At this point, always support the robot arm with your hand. Because pressing manual button will release the torque and the arm may fall under its own weight. Next, click the read angle button to record the servo position. If you want to change the action duration, adjust the duration field before clicking read angle. Finally, check that the new action has been added to the action list. Once you have saved the servo positions, you can now run the action. Simply click on the specific action in the action list to select it. Then press the run button and the robot will execute the motion you recorded. If you check the loop option, the action will repeat continuously. Finally, after recording several servo positions, we can save and replay a full trajectory. To do this, first click the Save Action File button. Next, in the Action Groups section, select the Saved Action File. Then, click Run Action to replay the trajectory. One important note is that please do not change the save directory. Keeping the default path ensures that the software can correctly find and run your action file. In the last step of direct teaching, we can replay a saved waypoint trajectory using the action group node. To do this, pass the name of your saved action file to the function execute action group inside runActionGroup.py. Since the action file is already saved in the default directory, please do not change the path. Finally, run the command Python 3 runActionGroup.py to check and replay your direct teaching. So, for this week's evaluation, all tasks must be completed during the lab session, and we will evaluate your work on the spot. Once your evaluation is finished, you're free to leave. So the total score for week 1 is 3 points. For kinematics is worth 1 point, and inverse kinematics is worth 2 points. Please remember the okay. And finally, let me give you some additional guidelines. After you implemented for the inverse kinematics, run Python 3 eval fk.py and Python 3 eval ik.py to verify your code. If the terminal output does not show 0.000, you will not receive points. Also, please modify only the sections marked with to do inside kinematics.py. Do not make any other changes. The remaining tasks are not graded, but I highly recommend you to try them out. And one important note, the robot may malfunction if the battery is discharged. So whenever possible, please use the charger inside the white box during your job. Okay, this is the end of the